Welcome to Quiet Universe, where we explore the deepest mysteries of the cosmos. Today, we journey into the mind-bending world of cosmic strings, extraordinarily thin yet infinitely long structures that could reshape our understanding of the universe. Let's dive into the incredible possibilities and profound implications these elusive relics of the early universe might hold. Imagine a universe where the fabric of reality is stretched and twisted by objects so bizarre, they defy our understanding of physics. These are cosmic strings, theoretical entities that, if they exist, would be some of the most extraordinary objects in the cosmos. The concept of cosmic strings emerges from the study of the early universe, a time of immense heat and density, where the fundamental forces of nature were unified in ways we can only speculate about today. As the universe expanded and cooled, it underwent a series of phase transitions, moments where the fundamental nature of reality changed. During these transitions, it's possible that imperfections formed in the fabric of space itself, giving birth to cosmic strings. Cosmic strings are not like the strings you might find in everyday life. They are one-dimensional objects, meaning they have length but no width or height. But don't let their apparent simplicity fool you. These strings could be infinitely long, stretching across the entire universe, yet they would be incredibly thin, much thinner than a proton. Their thickness is so small that it's beyond the reach of current technology to measure directly. However, despite this thinness, cosmic strings would be immensely dense. A meter-long segment of a cosmic string could weigh as much as a mountain. This combination of infinite length and extreme density is almost impossible to fathom. It challenges our understanding of what matter is and how it can be distributed in the universe. How can something so thin carry so much mass? This question is one of the many puzzles that cosmic strings present. The immense mass of cosmic strings would have profound effects on the space around them. In Einstein's theory of general relativity, mass and energy curve spacetime and cosmic strings, with their colossal mass, would create deep, narrow grooves in the fabric of space. This warping of spacetime would cause light to bend around the strings, leading to gravitational lensing effects. Imagine looking at a distant galaxy and seeing its light bent into strange shapes, double images, arcs, or even complete circles of light known as Einstein rings. These visual phenomena would be a direct consequence of a cosmic string's influence, despite the string itself being invisible. The idea that a one-dimensional object, so thin that it's nearly undetectable, could exert such a powerful gravitational force is astonishing. It stretches the imagination to think about how such a structure could exist and interact with the universe. But the effects of cosmic strings don't stop there. If two strings were to intersect or if a single string looped back on itself, they could create what are known as kinks or cusps. These are points where the string's energy is concentrated, and they can have dramatic consequences. The energy stored in these kinks could be released in the form of gravitational waves, ripples in the fabric of spacetime that travel across the universe. Gravitational waves are themselves a relatively recent discovery, and the idea that such waves could be generated by the interactions of cosmic strings adds a new layer of complexity to our understanding of these phenomena. The release of energy from these kinks and cusps could be immense, far greater than anything we can produce on Earth. The sheer amount of energy that could be unleashed by something so small and thin is mind-boggling, pushing the limits of what we know about the universe. One of the most intriguing possibilities associated with cosmic strings is the idea that they could connect different regions of space. In some theories, a cosmic string could act as a kind of cosmic highway, linking distant points in the universe. This concept is reminiscent of the idea of a wormhole, but in a one-dimensional form. If cosmic strings do act as shortcuts through space, they could potentially allow for faster-than-light travel, or at least offer a way to traverse vast distances more quickly than would otherwise be possible. This challenges our conventional understanding of distance and travel in the universe. It opens up the possibility that the structure of the cosmos is far more interconnected than we currently believe. Cosmic strings are thought to be relics from the early universe, formed during those first few moments after the Big Bang, when the universe was still incredibly hot and dense. As such, they could carry information about the conditions of the universe at that time. Understanding cosmic strings could give us profound insights into the nature of the universe's birth and the forces that shaped it. They could provide clues about how the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, unified and then separated as the universe cooled. This is not just a matter of theoretical interest. It's a way of peering back in time to the very origins of everything we see around us today. The existence of cosmic strings is predicted by certain grand unified theories, GUTs, in physics. These theories attempt to unify the fundamental forces into a single framework, and cosmic strings could be evidence that such unification is possible. If we were to detect a cosmic string, it would be a monumental discovery, confirming aspects of these theories and providing a link between the macroscopic universe we observe and the microscopic world of particle physics. It would be as if we had found a thread connecting the vast, sprawling cosmos with the tiny, invisible particles that make up everything we know. The implications of such a discovery would be profound, altering our understanding of the universe at the most fundamental level. Yet, for all their potential significance, cosmic strings remain elusive. Despite their theoretical importance and the massive effects they could have on their surroundings, detecting them is incredibly difficult. Their thinness and the subtlety of their gravitational effects make them hard to observe directly. Scientists have searched for the telltale signs of cosmic strings, gravitational lensing effects, gravitational waves, and other phenomena, but so far, the evidence remains circumstantial. This difficulty of detection adds to the mystery of cosmic strings. They could be out there, stretching across the universe, shaping the cosmos in ways we can barely imagine, yet hidden from our view. The existence of cosmic strings also raises the possibility of other exotic objects, like monopoles or domain walls, which are also predicted by certain theories of the early universe. These objects, like cosmic strings, would challenge our understanding of the fundamental nature of reality. The potential for these objects to exist adds another layer of mystery to the already complex and enigmatic nature of cosmic strings. It suggests that the universe is filled with structures and phenomena that we have yet to discover, each one pushing the boundaries of what we know. Cosmic strings, with their infinite length, immense density, and profound effects on spacetime, represent one of the most mind-boggling concepts in cosmology. They challenge our understanding of the universe and push the boundaries of theoretical physics. Whether they exist or not, the study of cosmic strings forces us to confront the limits of our knowledge and to consider the possibility that the universe is far stranger and more complex than we ever imagined. Imagine a thread so thin it makes a human hair look like a thick rope by comparison. Now imagine that this thread is not just a few inches or feet long, but could potentially stretch across the entire universe, from one end to the other. Such is the nature of cosmic strings, theoretical objects born in the very early moments of the universe's existence. These cosmic strings, if they indeed exist, challenge our understanding of what is physically possible, pushing the boundaries of both imagination and physics. Cosmic strings are not objects we can easily picture because they defy the usual rules of our everyday world. They are thought to be one-dimensional, meaning they have length but no width or height in any conventional sense. If you could somehow look at one directly, it would be so thin that you wouldn't be able to see it with the naked eye. It's thinner than the smallest particle we can currently observe, far thinner than an atom, and yet it could be infinitely long. The idea of something being infinitely long is already difficult to comprehend. We are used to things having ends, limits, and boundaries. But a cosmic string could stretch across the entire universe, never ending, a continuous line of pure energy. Now, consider the density of this string. In our everyday world, we think of dense things as being heavy and solid, like a rock or a block of metal. But cosmic strings take this concept to an extreme. Even though they are incredibly thin, they are also incredibly dense. In fact, they are so dense that just 1 meter of a cosmic string could weigh as much as a mountain. That's a staggering amount of mass packed into a space so small it defies our normal experiences. Imagine holding a meter-long piece of string that weighs millions of tons. It's not something that fits easily into our understanding of the physical world. This combination of infinite length and immense density is where the true strangeness of cosmic strings lies. In the realm of physics, we're used to thinking of mass as something that takes up space, something with volume. A rock, for example, has a certain mass and takes up a certain amount of space. But cosmic strings flip this idea on its head. They are incredibly massive, but they take up virtually no space at all. The density of these strings is beyond anything we've encountered in the universe, other than perhaps inside black holes. It's difficult to even find an analogy in the natural world because nothing we know of behaves quite like a cosmic string. The existence of such an object would have profound implications for our understanding of the universe. For one, the gravitational effects of a cosmic string would be unlike anything else. Mass, according to Einstein's theory of general relativity, bends space and time around it. This is how gravity works. The more massive an object, the more it bends space and time, creating a gravitational field. A cosmic string, with its immense density, would create a deep groove in the fabric of spacetime, like a razor-thin cut stretching across the cosmos. Anything that came near it would feel this gravitational effect, potentially warping the path of light in the orbits of stars. Because of their incredible mass, cosmic strings would exert a gravitational pull that, while confined to a narrow area, would be tremendously strong. However, the nature of this pull would be strange. Unlike a planet or a star, which has a gravitational field that pulls equally in all directions, the gravitational field of a cosmic string would be concentrated along its length. This would create a sort of gravitational canyon, a narrow, but infinitely long, region where gravity is incredibly intense. If you were to approach this string, you wouldn't fall toward it like you would with a planet. Instead, you might be pulled along its length, like water flowing in a river. This concept is so far removed from anything in our everyday experience that it's difficult to fully grasp. How can something be so massive yet so thin? How can it be infinitely long, yet confined to a dimension we can't even see? These are the kinds of questions that cosmic strings force us to ask, and they don't have easy answers. They require us to rethink what we know about mass, space, and the very nature of reality. In the context of the universe, the existence of cosmic strings would suggest that the cosmos is far stranger and more complex than we currently understand. These strings could be remnants from the early universe, formed in the first moments after the Big Bang, when the universe was still a seething, chaotic place. Back then, the universe was incredibly hot and dense, and the laws of physics as we know them didn't yet apply in the same way. As the universe cooled and expanded, it underwent a series of phase transitions, much like how water turns into ice. During these transitions, it's possible that cosmic strings formed as defects in the fabric of space itself. If cosmic strings do exist, they would be some of the oldest objects in the universe, predating stars, galaxies, and even atoms. They would be relics from a time when the universe was a vastly different place, carrying within them the secrets of that early, violent period. Studying them could provide us with insights into the conditions of the early universe and the fundamental forces that shaped everything we see today. But cosmic strings are not just relics, they are also incredibly powerful. Their immense density means that they could release vast amounts of energy, potentially even in the form of gravitational waves, ripples in spacetime that travel across the universe. If two cosmic strings were to collide or loop back on themselves, the energy released could be enormous, sending shockwaves through the fabric of space itself. This energy release would be far beyond anything we could produce on Earth, hinting at the raw power contained within these seemingly thin and insignificant strings. The very idea of cosmic strings stretches our imagination to its limits. They are objects that defy our understanding of physics, combining infinite length with immense density in a way that seems almost paradoxical. Yet, they are not just theoretical curiosities. If they exist, they could hold the key to understanding some of the deepest mysteries of the universe, how it began, how it evolved, and what it is ultimately made of. In the end, cosmic strings are a reminder of how much we still don't know about the universe. They challenge us to think beyond the confines of our everyday experience, to imagine a cosmos that is far more complex and mysterious than we ever imagined. Whether or not we ever find direct evidence of these strange objects, the mere possibility of their existence forces us to confront the limits of our knowledge and to keep searching for answers in the vast, uncharted reaches of the cosmos. Imagine a universe where space and time are not just abstract concepts, but a flexible, dynamic fabric that can be twisted, bent, and stretched by the presence of mass and energy. This is the reality that Einstein's theory of general relativity presents to us, a world where gravity is not merely a force, but the manifestation of spacetime itself curving in response to matter. In this context, cosmic strings, if they exist, would be among the most fascinating and powerful entities in the universe, capable of warping spacetime in ways that are both strange and beautiful. Cosmic strings are theoretical objects that, despite being incredibly thin, possess an immense amount of mass. Their density is so extreme that it's almost beyond comprehension, with just a meter of string potentially weighing as much as a mountain. But what makes cosmic strings truly extraordinary is the effect they would have on the space around them. Their mass would be so concentrated that they would carve deep, narrow grooves into the fabric of spacetime. These grooves would create a gravitational field unlike anything we're familiar with, a field so intense and so focused that it would bend light itself. When light from a distant star or galaxy passes near a cosmic string, it doesn't follow a straight path. Instead, the light is pulled into the groove created by the string's gravity, causing it to bend. This bending of light, known as gravitational lensing, is one of the most remarkable predictions of general relativity. In the presence of a cosmic string, gravitational lensing would produce visual effects that are as stunning as they are strange. Imagine looking at a distant galaxy through a telescope and seeing its image split into two, or even more bizarre, seeing a perfect ring of light, a phenomenon known as an Einstein ring, encircling a dark center where the string lies. These are the kinds of effects that a cosmic string could produce, warping the very light that travels through space and revealing its presence in the most extraordinary way. The idea that a thin, one-dimensional object, something so small and simple in appearance, could have such a dramatic impact on spacetime is astonishing. We're used to thinking of massive objects like planets, stars, and black holes as the primary sources of gravitational fields. These objects are vast, solid, and easily visible. But a cosmic string turns this expectation upside down. Despite being almost impossibly thin, a cosmic string's gravitational field would be incredibly strong, enough to alter the path of light from distant stars and galaxies. It's a reminder that in the universe, mass and gravity are not always tied to size or visibility. Even the smallest, thinnest objects can wield tremendous power. The effects of gravitational lensing by a cosmic string would be unlike any other form of lensing we observe. Typically, gravitational lensing occurs around massive objects like galaxies or black holes, which have relatively large spherical gravitational fields. These fields cause the light to bend gradually, often creating arcs or distorted images of background objects. But the lensing caused by a cosmic string would be different. Because the string's gravitational field is concentrated along a very narrow line, the light would bend sharply, creating sudden, dramatic shifts in the images we see. The result could be double images, where the same object appears twice on either side of the string, or complete rings of light, where the image is wrapped around the string in a perfect circle. These effects are not just visually striking, they also offer a unique way to detect and study cosmic strings. In a universe filled with countless stars and galaxies, spotting a cosmic string directly might seem impossible. After all, they are so thin that they would be practically invisible to our most powerful telescopes. But by looking for these unusual patterns of light, the double images, the Einstein rings, we could potentially identify the presence of a cosmic string. It's as if the string leaves behind a signature in the light of the universe, a mark that reveals its existence without us ever needing to see the string itself. The implications of this are profound. If we were to observe such gravitational lensing effects in the sky, it would be a clear sign that cosmic strings exist, confirming a key prediction of certain theories in cosmology and particle physics. These strings are thought to be remnants from the early universe, formed during the first fractions of a second after the Big Bang. Detecting them would not only provide direct evidence for their existence, but also offer a glimpse into the conditions of the universe at its birth. It would be like finding a fossil from a time when the universe was young and chaotic, a time when the fundamental forces of nature were still emerging, and the universe was far different from what we see today. But the story doesn't end with the detection of cosmic strings. The gravitational lensing they produce could also help us learn more about the structure and evolution of the universe. By studying how light bends around these strings, we could map out their distribution across the cosmos, gaining insights into the large-scale structure of the universe. We could also use these observations to test our theories of gravity and spacetime, probing the limits of general relativity and exploring the possibility of new physics beyond what we currently know. In this way, cosmic strings could become powerful tools for understanding the cosmos, revealing hidden aspects of the universe that would otherwise remain beyond our reach. One of the most fascinating aspects of cosmic strings and their gravitational lensing effects is the way they challenge our intuition about space and time. We're used to thinking of space as a vast, empty expanse, and time as a steady, unchanging flow. But in the presence of a cosmic string, these notions are turned on their head. Space becomes something that can be twisted and bent, something that can be shaped by the presence of mass in ways that are almost alien to our everyday experience. Time, too, is affected, as the warping of spacetime around the string alters the paths of objects moving through it, potentially even affecting the rate at which time passes in the string's vicinity. The more we think about the effects of cosmic strings, the more they push us to reconsider our understanding of the universe. They are objects that defy simple categorization, blending elements of the very large, their potential infinite length, with the very small, their incredibly thin width, and the incredibly massive, their immense density, with the nearly invisible. And yet, despite their strange and complex nature, they could be out there right now, silently shaping the light that reaches us from distant stars and galaxies, leaving behind patterns in the sky that hint at their presence. In a sense, cosmic strings are like cosmic whispers, faint but persistent clues to a deeper, more intricate reality than we currently comprehend. Their ability to warp spacetime and create gravitational lensing effects is just one aspect of their potential influence. As we continue to explore the universe and refine our observations, we may one day be able to detect these elusive strings and unravel the mysteries they hold. Until then, the idea of cosmic strings remains one of the most intriguing and mind-bending possibilities in modern cosmology, a reminder that the universe is full of surprises, waiting to be discovered and understood. In the vast mysterious expanse of the universe, cosmic strings are among the most enigmatic theoretical objects that have captured the imagination of physicists and cosmologists alike. These one-dimensional, incredibly thin entities are hypothesized to be remnants from the early universe, stretching across vast distances and possessing an unimaginable density. However, what makes cosmic strings even more fascinating is their potential to release enormous amounts of energy, especially when they form kinks or cusps. Picture the universe in its infancy, a seething cauldron of energy where matter and energy were not yet distinct. It was during this chaotic time that cosmic strings are believed to have formed, as the universe underwent various phase transitions. Just as cracks form in ice as it freezes, cosmic strings might have formed as the universe cooled and its fundamental forces separated. These strings, though infinitesimally thin, much thinner than an atom, are thought to carry a colossal amount of energy. But their story becomes truly extraordinary when we consider what happens when these strings intersect or loop back on themselves. When two cosmic strings cross paths, they do not simply pass through each other like ghostly specters. Instead, they can become entangled, creating sharp bends and twists known as kinks. Imagine two strands of an impossibly fine thread that suddenly collide. Instead of smoothly crossing, they become tangled, forming tight knots. These knots or kinks are not just physical distortions, but are regions where the string's energy is highly concentrated. Similarly, when a single cosmic string loops back on itself, it can form a point of extreme curvature called a cusp. At these cusps, the string's energy is squeezed into an incredibly small space, creating conditions that are truly mind-boggling. The energy stored in these kinks and cusps is not merely a static feature, it is dynamic, potent, and potentially explosive. The immense energy density of a cosmic string means that when these kinks and cusps form, they can release this energy in a sudden burst. But this isn't energy as we commonly think of it, light, heat, or even kinetic energy. Instead, the energy from these kinks and cusps is released in the form of gravitational waves, ripples in the fabric of spacetime itself. Gravitational waves are one of the most extraordinary predictions of Einstein's general theory of relativity. They are disturbances in spacetime that propagate outward from a source, much like the ripples that spread across a pond when a stone is thrown into it. In the case of cosmic strings, these waves are not caused by massive objects like colliding black holes or neutron stars, but by the sudden release of energy from these tiny, one-dimensional strings. The thought that something as small and thin as a cosmic string could generate gravitational waves is astonishing, yet it is precisely the concentrated energy in these kinks and cusps that makes it possible. The release of gravitational waves from cosmic strings would be a cataclysmic event on a cosmic scale, albeit one that would occur in the silent, dark reaches of space. These waves would carry energy across the universe, warping spacetime as they travel. If we were to detect such a wave, it would be like hearing a distant echo from the birth of the universe, a signal from a time when the cosmos was still young and its fundamental structures were just beginning to form. The possibility of detecting these waves has intrigued scientists, as it would provide direct evidence of the existence of cosmic strings and offer a unique glimpse into the earliest moments of the universe. However, the idea of cosmic strings releasing such immense energy also challenges our understanding of energy and matter. In our everyday experience, energy is associated with large tangible objects, moving cars, burning fires, or the heat of the sun. But cosmic strings, which are thinner than an atom and invisible to the naked eye, defy this notion. They remind us that the universe operates on scales and in ways that are far beyond human intuition. The energy locked within these strings, especially at their kinks and cusps, is a testament to the incredible density and tension that these objects could possess. To put it into perspective, consider the fact that a meter of cosmic string could weigh as much as a mountain. Now imagine the energy stored in a kink or cusp, where this immense mass and tension are concentrated into a tiny region of space. The release of this energy as gravitational waves would be on a scale that dwarfs anything we could imagine. It's a reminder that the universe is filled with phenomena that are not only beyond our current ability to observe, but also beyond our ability to fully comprehend. The study of cosmic strings and the potential energy release from kinks and cusps is more than just an exercise in theoretical physics, it is an exploration of the boundaries of our understanding of the universe. It challenges us to think about energy, gravity, and spacetime in new ways, pushing the limits of what we know and what we can imagine. The fact that these strings might generate gravitational waves also opens up new possibilities for detecting them. Gravitational wave detectors like LIGO and Virgo have already opened a new window into the universe, allowing us to observe events that were previously invisible. If cosmic strings exist and if they release energy through kinks and cusps, then we might one day detect these events, adding a new chapter to our understanding of the cosmos. But there is also a profound philosophical aspect to this idea. The existence of cosmic strings and the energy they could release speaks to the incredible complexity and richness of the universe. It suggests that the universe is not just a vast empty space filled with stars and galaxies, but a dynamic evolving entity where even the smallest, most seemingly insignificant objects can have a profound impact. It reminds us that the universe is far more intricate and interconnected than we might think, with processes and phenomena that are constantly shaping the cosmos in ways we are only beginning to understand. In the end, the concept of energy release from kinks and cusps in cosmic strings is a striking example of how theoretical physics can reveal the deep and often surprising nature of reality. It challenges us to look beyond the visible and the tangible, to consider the possibility that the universe is filled with forces and objects that, while invisible to us now, play a crucial role in its ongoing evolution. Whether or not cosmic strings exist, the very idea of them, and the potential energy they might release, opens our minds to the vast, mysterious, and still largely unknown universe we inhabit. The cosmos is a realm of infinite possibilities, a vast expanse where the laws of physics as we understand them are both challenged and extended into realms of speculative wonder. Among the most tantalizing of these possibilities is the notion that cosmic strings, those elusive, one-dimensional remnants of the early universe, might serve as conduits between distant regions of space. This concept, akin to the idea of wormholes but distinct in its own right, suggests a universe where the vastness of space might be traversed not by the conventional, tedious journey through the void, but by taking a shortcut along the spine of a cosmic string. In the conventional view of the universe, space is a vast continuous expanse. Even at the speed of light, the distances between stars, galaxies, and even more remote regions are incomprehensibly large. The very idea of traveling across these distances, whether by a spacecraft or a beam of light, is daunting, constrained by the limits of both technology and the fundamental speed limit imposed by the universe itself. Yet, the concept of cosmic strings offers a different perspective, a radical departure from the constraints of conventional space travel. Imagine, if you will, a thread stretched taut across the fabric of space, so thin that it is invisible to all but the most sensitive instruments, yet so dense that it warps the very space around it. This thread is a cosmic string, a relic from the earliest moments of the universe, possibly stretching across vast distances, connecting regions of space that, by any other means, would seem impossibly far apart. The idea that such a string could link different regions of space is not just speculative but revolutionary, suggesting that the universe may have built-in shortcuts, cosmic highways that could, in theory, be traversed to bridge the immense gulfs of space in a way that defies our current understanding of distance. The comparison to a wormhole is inevitable, yet the analogy is imperfect. Wormholes, as conceived in the framework of general relativity, are tunnels through spacetime that connect two distant points, effectively allowing for faster-than-light travel across the universe. Cosmic strings, however, are not tunnels but more like tightropes, narrow, one-dimensional paths that stretch across space. The difference may seem subtle, but it is profound. A wormhole suggests a bridge between 2 points, a passage that allows for instantaneous travel through an otherwise impassable barrier. A cosmic string, on the other hand, implies a continuous, albeit incredibly narrow, path that could be followed to reach distant regions of space. But how might such a string actually function as a cosmic highway? The key lies in the way that cosmic strings interact with spacetime. Due to their immense mass and the extreme tension under which they exist, cosmic strings are capable of warping the space around them. This warping is not just a local phenomenon, but can extend over vast distances, effectively altering the geometry of space in their vicinity. If two regions of space are connected by a cosmic string, the string could create a kind of shortcut, reducing the effective distance between these regions in a way that bypasses the usual constraints of space travel. To grasp this idea, consider how a piece of paper can be folded. If you draw two dots on opposite ends of the paper, the straight line distance between them is significant. However, if you fold the paper so that the dots overlap, the distance between them is reduced to zero. In a somewhat analogous fashion, a cosmic string could effectively fold the space around it, creating a pathway that links two distant regions much more closely than they would otherwise be. Traveling along this string would allow for a journey that, in conventional terms, would be impossible or take an unfathomable amount of time. Yet, the potential of cosmic strings as cosmic highways goes beyond mere travel. If such strings do exist and connect different regions of space, they might also provide insights into the fundamental structure of the universe. The existence of these connections could imply that space is not as continuous and uniform as we might think, but is instead a complex interconnected web, with cosmic strings serving as the threads that hold it all together. This idea challenges our conventional understanding of space as a vast empty void and suggests instead that it is a dynamic interconnected entity where distances are not always what they seem. The implications of this are staggering. If cosmic strings could indeed link different regions of space, they might allow for communication or even the transfer of matter and energy across vast distances in ways that would be impossible by any other means. This could revolutionize our understanding of the universe, opening up possibilities for exploration and interaction that are currently confined to the realm of science fiction. It also raises profound questions about the nature of space itself. What does it mean for two regions of space to be connected by a cosmic string? Is space truly continuous, or is it a patchwork of interconnected regions, with cosmic strings serving as the seams that hold it all together? Of course, the idea of cosmic strings as cosmic highways is still speculative, a hypothesis that has yet to be confirmed by observation. The detection of cosmic strings, let alone their use as pathways across the universe, remains one of the most elusive goals in modern cosmology. Yet, the very possibility is enough to inspire wonder and curiosity. It suggests a universe that is not just vast, but also fundamentally interconnected in ways that we are only beginning to understand. In contemplating cosmic strings, we are reminded of the limits of our current knowledge and the boundless possibilities that lie beyond. The idea that such strings could connect different regions of space challenges us to rethink our understanding of distance, travel, and the very nature of space itself. It invites us to imagine a universe where the impossible becomes possible, where the vast distances between stars and galaxies can be bridged by following a narrow, invisible path across the cosmos. It is a vision of a universe that is not just vast and empty but dynamic, interconnected, and full of possibilities that we have only begun to explore. The concept of cosmic strings as cosmic highways also touches on deeper philosophical questions about the nature of reality. If such strings do exist, they would suggest that the universe is not just a random, chaotic expanse, but a carefully woven fabric with connections that transcend our usual understanding of space and time. It would imply that the universe is a more ordered, structured entity than we might have thought, with cosmic strings serving as the threads that bind it all together. In the end, the idea of cosmic strings as cosmic highways is a powerful reminder of the mysteries that still lie at the heart of the universe. It challenges us to look beyond the familiar and to consider the possibility that the universe is far more complex and interconnected than we can currently comprehend. Whether or not cosmic strings exist, the very idea opens up new avenues of thought and exploration, inviting us to imagine a universe where the boundaries of space and time are not fixed but fluid, where the vast distances that separate us from the stars might one day be bridged by following a cosmic string across the void. In the vast and mysterious expanse of our universe, there are secrets that stretch back to the very beginning of time itself. Among these secrets, cosmic strings stand as one of the most enigmatic and intriguing relics from the early universe. These one-dimensional defects, if they exist, are not just fascinating for their peculiar properties, but for what they could reveal about the universe's infancy, an era that remains largely shrouded in mystery. The story of cosmic strings begins in the aftermath of the Big Bang, that momentous event roughly 13.8 billion years ago that set the universe into motion. The Big Bang was not just an explosion in the conventional sense, but the rapid expansion of space itself, filled with a hot dense soup of particles and energy. During the first fraction of a second, the universe was in a state of flux, where the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces, were still merging and differentiating. It was in this chaotic, high-energy environment that cosmic strings might have been born. To understand how cosmic strings could have formed, one must delve into the concept of symmetry breaking. In the early universe, it is theorized that all the fundamental forces were unified, governed by a single, overarching symmetry. However, as the universe cooled and expanded, this symmetry began to break, causing the forces to separate and behave differently. This process is akin to water freezing into ice, where the once uniform liquid water forms distinct and structured crystals. In the universe, as the fundamental forces separated, they could have left behind defects in the fabric of space-time, cosmic strings being one such defect. Imagine the universe as a vast field of energy, with cosmic strings acting as thin thread-like imperfections in this field. These strings would be incredibly thin, much thinner than an atom, yet incredibly dense, with a single meter of string potentially weighing as much as a mountain. The density and tension within these strings would be immense, stretching across vast distances, potentially even across the entire universe. These properties make cosmic strings not just interesting, but fundamentally different from any other known structure in the universe. But why do cosmic strings matter? What makes them more than just a theoretical curiosity? The answer lies in the unique role they might play as relics from the early universe. If cosmic strings do exist, they are direct witnesses to the conditions that prevailed in the moments after the Big Bang. They could hold within them clues about the state of the universe when it was still in its infancy, when temperatures and energies were far beyond anything we can recreate on Earth. Understanding cosmic strings could provide a window into a time when the universe was just a fraction of a second old, a time when the laws of physics as we know them were still taking shape. The study of cosmic strings might reveal details about how the fundamental forces separated from one another, how particles acquired mass, and how the universe transitioned from a hot, dense plasma to the vast and structured cosmos we see today. The implications of this are profound. By studying cosmic strings, scientists could potentially unlock secrets about the very origins of the universe, offering insights into some of the most fundamental questions in cosmology and particle physics. For instance, cosmic strings could shed light on the nature of dark matter, the mysterious substance that makes up most of the universe's mass but has yet to be directly observed. They could also provide evidence for or against certain grand unified theories, GUTs, which attempt to reconcile the different fundamental forces under a single framework. The existence of cosmic strings would also have implications for our understanding of space-time itself. As immensely dense objects, cosmic strings would exert a significant gravitational influence, warping the fabric of space-time around them. This could lead to phenomena such as gravitational lensing, where light from distant stars and galaxies bends around the string, creating distinctive visual effects like double images or even entire rings of light. These effects would not only be visually stunning, but would also serve as indirect evidence for the existence of cosmic strings, offering astronomers a new tool to probe the depths of the universe. However, despite their potential importance, cosmic strings remain elusive. Their thinness and the subtlety of their gravitational effects make them incredibly difficult to detect. Over the years, astronomers and physicists have searched for signs of cosmic strings, scanning the sky for the telltale signs of gravitational lensing or other effects that could indicate their presence. Yet, so far, direct evidence for cosmic strings has remained out of reach, leaving them as tantalizing possibilities rather than confirmed realities. This elusiveness only adds to the allure of cosmic strings. The idea that such powerful and fundamental objects could exist, hidden from our view, challenges our understanding of the universe and pushes the boundaries of theoretical physics. It also serves as a reminder of how much we still have to learn about the cosmos. The universe is vast and filled with mysteries, many of which remain just out of reach, waiting for the right observation or the right experiment to bring them into the light. In recent years, advances in technology and observational techniques have renewed interest in the search for cosmic strings. Projects like the Laser Interferometer Gravitational Wave Observatory, LIGO, and its counterparts around the world have opened up new possibilities for detecting the gravitational waves that might be produced by cosmic strings. If two strings were to intersect or form a loop, they could release bursts of gravitational waves, rippling through space-time and potentially being detected here on Earth. Such a discovery would not only confirm the existence of cosmic strings, but also revolutionize our understanding of the universe's earliest moments. In many ways, cosmic strings represent the frontier of our knowledge about the universe. They are relics from a time when the universe was young and filled with possibilities, a time when the laws of physics were still being written. Studying cosmic strings could bring us closer to understanding the birth of the universe, the forces that shaped it, and the nature of the reality we inhabit. As we continue to explore the cosmos, searching for evidence of cosmic strings and other relics from the early universe, we are not just looking into the past, we are also looking into the future. Each discovery brings us closer to a deeper understanding of the universe, its origins, and its ultimate fate. In this quest, cosmic strings are more than just theoretical constructs, they are the threads that could weave together some of the most profound mysteries of existence. The quest to understand the fundamental nature of the universe has long been one of humanity's most profound endeavors. At the heart of this quest lies the pursuit of a unified theory, a framework that can seamlessly connect the diverse forces of nature under a single, coherent model. For decades, physicists have sought to achieve this through the development of grand unified theories, GUTs. These theories aim to bridge the gap between the different fundamental forces that govern the universe. The electromagnetic force, the weak nuclear force, and the strong nuclear force. While gravity remains elusive within this framework, GUTs represent a bold step toward unraveling the underlying principles that dictate the behavior of the cosmos at both the largest and smallest scales. In this grand pursuit, cosmic strings emerge as more than just theoretical curiosities, they become essential players, potentially holding the key to validating these unifying concepts. The existence of cosmic strings, as predicted by certain GUTs, could offer tangible evidence that these ambitious theories are more than mere mathematical constructs, they could be true descriptions of our universe. To understand the connection between cosmic strings and grand unified theories, we must first delve into the nature of the forces these theories seek to unify. In the everyday world, we are most familiar with gravity, which pulls objects toward one another, and electromagnetism, which governs the behavior of charged particles and is responsible for electricity, magnetism, and light. Less familiar to most are the strong and weak nuclear forces, which operate at the subatomic level. The strong force binds protons and neutrons together in the nucleus of an atom, while the weak force is responsible for processes like radioactive decay. Each of these forces is currently described by its own distinct theory within the broader framework of the Standard Model of particle physics. However, the Standard Model, despite its success in explaining a wide range of phenomena, leaves many questions unanswered. It treats the four forces as separate entities, each with its own set of rules, and it fails to incorporate gravity in a satisfactory way. Moreover, the model requires a variety of seemingly arbitrary parameters to work, leading physicists to suspect that a deeper, more fundamental theory must exist, one that unifies these forces into a single, elegant framework. This is where grand unified theories come into play. GUTs propose that at extremely high energies, far beyond anything we can currently achieve in particle accelerators, the electromagnetic, weak, and strong forces are not distinct, but are instead manifestations of a single, unified force. As the universe cooled after the Big Bang, this unified force would have gradually broken apart into the three distinct forces we observe today. The breaking of this unified force is analogous to the way water freezes into ice, with the previously smooth and uniform field of energy forming distinct crystals or domains as it transitions into a lower energy state. During this symmetry breaking process, GUTs predict that various topological defects could have formed in the fabric of space-time, much like imperfections in a crystal lattice. Cosmic strings are one such defect, a one-dimensional, infinitely long structure that could arise naturally during the phase transitions that occurred in the early universe as the grand unified force splintered into its constituent parts. These strings would be incredibly thin, yet enormously dense, stretching across vast expanses of the universe. The formation of cosmic strings in the context of GUTs is a fascinating interplay between particle physics and cosmology. If such strings exist, they would be relics from a time when the universe was just a fraction of a second old, providing a direct link to the conditions that prevailed during the epoch of grand unification. Observing a cosmic string would therefore be like finding a fossil from the early universe, a tangible piece of evidence that could validate the predictions made by GUTs. The implications of such a discovery would be profound. First and foremost, it would provide strong support for the idea that the fundamental forces of nature were indeed unified at high energies, as GUTs propose. This would help bridge the gap between the macroscopic world of cosmology and the microscopic world of particle physics, offering a more cohesive understanding of the universe's evolution from the Big Bang to the present day. It would also suggest that the complex and seemingly arbitrary parameters of the Standard Model are not random, but are the result of the universe's journey from a highly symmetric, unified state to the broken, lower energy state we observe today. Furthermore, the detection of cosmic strings would open up new avenues for exploring the nature of the universe. These strings could serve as natural laboratories for studying physics at extreme energies and densities, far beyond what we can achieve in any man-made experiment. They might reveal new phenomena or interactions that could shed light on the unification of forces, or even hint at the elusive theory of quantum gravity, which seeks to incorporate gravity into the quantum realm. The existence of cosmic strings would also have implications for our understanding of the early universe's dynamics. Guts suggest that the early universe underwent a series of phase transitions as it cooled, much like water cooling and freezing into ice. These transitions would have been accompanied by the formation of cosmic strings and other topological defects, which could have influenced the evolution of the universe in subtle but significant ways. For instance, the gravitational effects of cosmic strings might have played a role in the formation of large-scale structures like galaxies and clusters of galaxies, seeding the density fluctuations that later grew into the cosmic web we observe today. Yet, despite their potential importance, cosmic strings remain elusive. Detecting them would require observing their subtle gravitational effects, such as the bending of light from distant stars and galaxies, a phenomenon known as gravitational lensing. Astronomers have been searching for these telltale signs for decades, scanning the skies for the characteristic patterns that cosmic strings might produce. So far, the evidence remains inconclusive, but the search continues, driven by the tantalizing possibility that cosmic strings could be the missing link in our quest to unify the forces of nature. In addition to gravitational lensing, another promising avenue for detecting cosmic strings lies in the field of gravitational wave astronomy. If cosmic strings exist, they could produce bursts of gravitational waves, ripples in the fabric of space-time, that could be detected by observatories like LIGO and its counterparts around the world. These waves would provide a direct signal of the string's existence, offering a new way to probe the early universe and the physics of grand unification. As we stand on the brink of new discoveries in both cosmology and particle physics, the connection between cosmic strings and grand unified theories remains one of the most intriguing and promising areas of research. The potential discovery of cosmic strings would not only validate the predictions of Guts, but also open up new frontiers in our understanding of the universe's origins and its fundamental laws. In this grand narrative, cosmic strings are more than just relics of the early universe. They are the threads that could weave together the disparate strands of our understanding into a unified whole. As we continue to explore the cosmos, seeking out these elusive structures, we move closer to uncovering the ultimate truths that govern our reality, truths that have remained hidden since the dawn of time. In the grand scheme of the universe, where massive celestial bodies like stars, planets, and black holes dominate our attention, the notion of cosmic strings, infinitely long, incredibly thin structures, presents a stark contrast. These hypothetical objects, if they exist, are not only fascinating for what they might reveal about the universe's early moments, but also for the incredible challenge they pose to detection. The idea that something so theoretically significant, capable of warping space-time and potentially influencing the large-scale structure of the cosmos, could remain hidden from our most sensitive instruments, is both frustrating and deeply intriguing. To understand why cosmic strings are so difficult to detect, we must first appreciate their unique properties. Unlike the familiar objects we observe in the night sky, cosmic strings are not made of ordinary matter. They are thought to be one-dimensional defects in the fabric of space-time itself, formed during the early universe's phase transitions, when the forces of nature began to separate and distinguish themselves. These strings would be incredibly thin, much thinner than a proton, yet immensely dense, with just a meter of cosmic string, potentially weighing as much as a mountain. Despite this density, their extreme thinness makes them practically invisible to conventional detection methods, which rely on observing light, particles, or other forms of radiation. One of the primary reasons cosmic strings are so elusive lies in the subtlety of their gravitational effects. In theory, a cosmic string's immense mass would have a profound impact on the space-time around it, creating a gravitational field strong enough to bend light. This phenomenon, known as gravitational lensing, could manifest in a variety of ways, such as double images of distant stars or galaxies, or even entire rings of light, often referred to as Einstein rings. Yet, despite the dramatic nature of these effects, detecting them in practice is far from straightforward. The difficulty arises from the fact that gravitational lensing by cosmic strings would produce effects that are both rare and easily mistaken for other astrophysical phenomena. For instance, the bending of light by a cosmic string would be much less pronounced than that caused by a massive galaxy or black hole, making the resultant images subtle and easily overlooked. Moreover, in a universe filled with countless other sources of gravitational lensing, such as galaxy clusters, it becomes a monumental task to distinguish the faint straight-line distortions that a cosmic string might cause from the myriad other lensing effects we observe. Another challenge in detecting cosmic strings is their presumed scarcity. If cosmic strings do exist, they are not expected to be common. The conditions necessary for their formation, specific phase transitions in the early universe, would likely have produced only a few such strings, scattered across the vastness of space. This scarcity means that even if cosmic strings are out there, the odds of one being close enough to Earth for us to observe its effects are slim. The universe is a vast place, and the distances between potential cosmic strings and our observational instruments could be so great that any gravitational effects they produce would be too faint to detect. Even more frustrating is the possibility that cosmic strings, despite their potential importance, might exist in forms that make them even more difficult to find. Some theoretical models suggest that cosmic strings could oscillate or form loops, emitting gravitational waves as they do so. These waves, ripples in space-time, could, in theory, be detected by observatories like LIGO, which has already observed gravitational waves from merging black holes and neutron stars. However, the gravitational waves produced by cosmic strings would likely be weaker and more sporadic than those from such massive events, making them harder to pick out from the background noise of the universe. Furthermore, the nature of gravitational wave detection itself adds to the difficulty. LIGO and similar observatories are incredibly sensitive, but they are also limited by the types of signals they can detect. Gravitational waves from cosmic strings would be of much lower frequency than those produced by black hole mergers, potentially placing them outside the current detection capabilities of our instruments. This means that even if cosmic strings are generating gravitational waves, we might not yet have the technology to observe them. The search for cosmic strings also faces challenges in terms of data interpretation. The universe is a noisy place, filled with countless sources of radiation, gravitational effects, and other phenomena that can mimic or obscure the signals we're looking for. Distinguishing the signature of a cosmic string from this cacophony requires not only advanced technology, but also sophisticated models and simulations to predict what such a signature would look like. Theoretical physicists and astronomers must work together, refining their models and comparing them with observational data in the hope of finding a match. This process is painstakingly slow and fraught with uncertainties, as even the most promising candidates can often be explained by more mundane phenomena. Despite these challenges, the pursuit of cosmic strings continues, driven by the tantalizing possibility of what their discovery could mean. For physicists, cosmic strings represent a direct link to the early universe, a relic from a time when the laws of nature were still being written. Their discovery would not only validate certain grand unified theories, but also provide new insights into the fundamental forces that govern our universe. This makes the search for cosmic strings a quest of profound significance, even if the odds of success seem slim. The difficulty of detecting cosmic strings is also a testament to the limits of our current understanding and technology. It highlights the fact that the universe is still full of mysteries, with many of its most profound secrets lying just beyond our reach. This can be frustrating, especially for scientists who have spent decades searching for evidence of these elusive objects, but it is also what makes the pursuit so compelling. The very fact that cosmic strings are so hard to find only adds to their allure, making them one of the most intriguing targets in modern astrophysics. As our observational techniques continue to improve, there is hope that we may eventually catch a glimpse of a cosmic string. Advances in gravitational wave detection, higher resolution telescopes, and more sophisticated data analysis methods all increase the chances that we might one day detect the subtle signs of these one-dimensional defects in space-time. Until then, the search for cosmic strings remains a reminder of the vastness of the universe and the challenges we face in understanding it. In the end, the difficulty of detecting cosmic strings is both a hurdle and an inspiration. It pushes scientists to develop new technologies, refine their theories, and explore the universe in ever greater detail. It challenges our assumptions about what is possible and reminds us that the universe is far more complex and mysterious than we might have imagined. And it keeps alive the hope that, somewhere out there in the vastness of space, these elusive threads of the cosmos are waiting to be discovered, ready to unravel the deepest mysteries of the universe. The universe, with all its vastness and complexity, is a playground of the strange and the unknown. For centuries, humanity has looked to the stars and beyond, trying to unravel the mysteries that lie hidden in the depths of space. One of the most fascinating prospects in this ongoing quest is the existence of cosmic strings, infinitely long, ultra-thin, and incredibly dense structures that, if real, could hold the secrets of the universe's earliest moments. But the implications of cosmic strings go far beyond their own enigmatic nature. Their existence could suggest the presence of other equally exotic and theoretical objects, such as magnetic monopoles or domain walls, each adding a layer of mystery to the already complex picture of the cosmos. The idea that cosmic strings might not be alone, but rather part of a broader family of topological defects, is both captivating and perplexing. These objects, predicted by certain theories of the early universe, are remnants from a time when the universe was still in its infancy, a seething cauldron of energy and forces struggling to find their equilibrium. As the universe cooled and expanded, it underwent a series of phase transitions, much like water freezing into ice, where different fields and forces froze out of the primordial soup. During these transitions, the fabric of space-time itself could have developed imperfections or defects, similar to the way imperfections form in crystals as they cool. Cosmic strings are one such defect, predicted by theories that attempt to describe the universe during its earliest moments, when the fundamental forces of nature were unified into a single force. But these strings are just one possibility among many. Depending on the specifics of the phase transitions that occurred in the early universe, other types of topological defects might have formed as well. One such possibility is the existence of magnetic monopoles, hypothetical particles that carry a single magnetic charge, either north or south, unlike ordinary magnets, which always have both a north and a south pole. Magnetic monopoles are predicted by certain grand unified theories, GUTs, which attempt to unify the strong, weak, and electromagnetic forces under one overarching framework. In these theories, monopoles could have formed as the universe cooled, and the unified force split into its constituent parts. If they exist, monopoles would be incredibly massive and carry a magnetic charge that could revolutionize our understanding of electromagnetism and particle physics. Their existence would also provide a key piece of evidence in support of GUTs, offering insight into the conditions of the early universe and the nature of the forces that govern it. Yet, despite decades of searching, no definitive evidence for magnetic monopoles has been found. This has led to speculation that if they do exist, they must be exceedingly rare or incredibly difficult to detect. Some theories suggest that the universe underwent a rapid expansion, known as inflation, shortly after the Big Bang. This inflationary period could have diluted the concentration of monopoles, spreading them out across the vastness of space and making them nearly impossible to find. However, the possibility remains that they are out there, hidden in the farthest reaches of the cosmos, waiting to be discovered. Domain walls are another type of topological defect that could have formed during the early universe's phase transitions. These walls are two-dimensional structures, like cosmic strings, but with an additional dimension. They could be thought of as the boundaries between different regions of space that underwent slightly different phase transitions, resulting in distinct physical properties on either side of the wall. Domain walls could have dramatic effects on the structure of the universe, influencing the distribution of matter and the formation of galaxies. The existence of domain walls, however, presents a theoretical problem. If they were too common or too massive, they could have catastrophic effects on the universe, possibly preventing the formation of galaxies and stars as we know them. For this reason, many cosmological models suggest that if domain walls did form, they must have quickly decayed or become extremely rare. Yet, the possibility that they could still exist somewhere in the universe remains, adding another layer of intrigue to the study of topological defects. The potential existence of these exotic objects, cosmic strings, magnetic monopoles, and domain walls, highlights the richness and complexity of the early universe. Each of these objects, if discovered, would provide a unique window into the universe's formative moments, offering clues about the fundamental forces that shaped it and the processes that led to its current state. Moreover, the discovery of any one of these objects would likely lead to new questions and avenues of research, deepening our understanding of the universe and its underlying principles. The hypothetical implications of cosmic strings and their kin also extend to the realm of theoretical physics, where they play a crucial role in testing and refining our models of the universe. For instance, the discovery of cosmic strings or magnetic monopoles would have profound implications for string theory, a framework that seeks to reconcile quantum mechanics with general relativity by positing that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. In string theory, cosmic strings could be macroscopic manifestations of these fundamental strings, providing a direct link between the abstract mathematical world of string theory and the observable universe. Furthermore, the existence of these objects could challenge our understanding of cosmology and the evolution of the universe. If cosmic strings or domain walls exist, they could have played a role in the formation of large-scale structures in the universe, such as galaxies and clusters of galaxies. Their gravitational effects could have influenced the distribution of matter in the universe, leading to the intricate cosmic web that we observe today. This would mean that the large-scale structure of the universe is not solely the result of gravitational interactions between ordinary matter, but also of these exotic objects, whose influence is woven into the very fabric of space-time. The discovery of cosmic strings or other topological defects could also have implications for our understanding of dark matter and dark energy, two of the most mysterious components of the universe. Dark matter is thought to make up about 27% of the universe's mass-energy content, while dark energy accounts for about 68%. Despite their importance, the nature of these substances remains unknown. Some theories suggest that cosmic strings or other defects could interact with dark matter or dark energy, offering clues about their properties and behavior. If this is the case, the study of cosmic strings could provide new insights into some of the biggest mysteries in cosmology. Yet, the very elusiveness of these objects adds to their mystique. The fact that they are so difficult to detect, despite their potentially massive effects on the universe, suggests that there may be aspects of the universe that are fundamentally beyond our current understanding. It challenges scientists to develop new theories, new technologies, and new ways of thinking about the cosmos. It also raises the tantalizing possibility that the universe is far more complex and layered than we can currently comprehend, with hidden dimensions and structures that we have yet to discover. The hypothetical implications of cosmic strings and their associated objects are, therefore, not just a matter of academic interest, they are a call to push the boundaries of our knowledge and explore the unknown. They remind us that the universe is a vast and mysterious place, full of surprises and challenges that await those who are willing to seek them out. And as we continue to search for cosmic strings, magnetic monopoles, and domain walls, we are not just looking for new objects in the sky, we are seeking to understand the very nature of reality itself. The journey may be difficult, and the answers elusive, but the potential rewards, a deeper understanding of the universe and our place within it, make the pursuit more than worthwhile. As we journey through the cosmos, delving into the mysteries of cosmic strings and the tantalizing possibilities they present, we're reminded of how much there is still to discover about our universe. The exploration of these enigmatic structures pushes the boundaries of our understanding and opens new doors to the unknown. If you enjoyed this deep dive into the wonders of the universe and want to explore even more mind-bending concepts, make sure to hit that subscribe button. Don't forget to give this video a thumbs up, it helps bring more cosmic insights straight to you. Stay curious, and until next time, keep looking up at the stars.